delay the lunch in 15 minutes.
No, I don't need more time.
Okay. Ready?
All right. So yesterday in the exercises that Henso was running, you were generating simulated data and then fitting models to those data using a Bayesian state space approach. So today I'm trying to explain what you actually did yesterday, talk about these Bayesian state space approaches. And this is kind of a big topic. It's difficult to cover it as part of this course. And that's partly why we decided to do it in this phase, that actually first in the exercises you do it in practice, then I explain what you did in theory, and then again in the exercises you do it in a practice. So we hope that after having done something, maybe you didn't fully understand every step what you did, but having done that in practice, it might be easier to follow this lecture. This kind of explains the concepts. And this is kind of very central lecture of our part of teaching, so I really hope that if there's anything you don't understand, just stop me and ask questions. We should have time for that, because I don't have too many slides, but we have 2 hours of time. So yesterday I started with this graph, kind of showing a simplification of the approaches that you can take to ecological modeling. For example, what Luca was talking about today was, oops, wrong button, was pretty much on, I think this is dead. It was about the upper part of the graph, where you make, assumptions, like you might assume that the animal has memory or doesn't have memory, and then you figure out what are the consequences of that assumption, like what kind of dynamics come out. That's kind of the mathematical modeling. The other approach here is this statistical modeling, which is in the most kind of stereotypic way done with linear models. You just fit some, relationship without any kind of mechanistic idea of the biology in the background. State space models, which I'm going to talk about today, they kind of combine these two approaches. This is one way. You're changing my slides. This is one way to visualize state space models. Let me first say that they have many names. People call them hidden Markov models, process-based models. I mean, these are not fully equivalent terms, but they are pretty much the same. So this is one way to visualize them. In the upper part, we have the kind of the biological process of interest, which we call the process model. In this case, it could be the movement model. So X here is the kind of the hidden truth, and then the process dynamics are denoted by these arrows. So in the case of animal movement, X of t would be the location of the animal at time t. Okay? We don't necessarily know it, we don't necessarily have data on it, but it exists. I mean, the animal was exactly in some location at time t. So that's why it's called the hidden truth. Okay? And the arrow here is the model, some stochastic process, for example a random walk model, which is describing the process, the movement process in this case. How do you get from a location at time t to a location at time t plus 1? So you can think that this upper part here is kind of the mathematical modeling part. Then in the lower part we have the letters y at t, t plus 1 and so on. They denote the observations, they denote the data. Okay? This is actually what we have seen. This is something that we haven't seen, but it exists. And there's an arrow from xt to yt. This is our observation model. Okay? So it includes the observations and the measurement error. I will make these more clear in a concrete example. And so the way the data are collected, that's pretty much the same as the observation model, and you can call this the statistical modeling part of the state space model. For example, when I presented this case study of butterfly movement in heterogeneous space, this upper part of the graph, that was my diffusion model in heterogeneous space with diffusion, habitat selection and mortality. That model would exist even if nobody went there and observed the butterflies. Whereas these stochastic links here, they denoted the observations, and they were parameterized in terms of the capture probability. That if you go there, if the butterfly would be there, then what's the probability that you see it? And the reason why these state space models or methods are becoming, I think, increasingly popular is that they are really flexible. It's just a general framework, not just for movement ecology, but any kind of dynamic processes. So they provide, at least conceptually, a unified framework in which to analyze data. So you might be interested in butterfly movements or in wolf movements, and you can think that the analysis you do are just variations of the same framework. So if you are interested in a butterfly, maybe a reasonable process model is that of habitat-specific diffusion, edge-mediated behavior. If you look at wolves, probably that's not enough. You have to add some other components into your movement model, like maybe edge following, edge avoidance, bias towards home range center, whatever is relevant in your study area. The type of data you can collect is very different because you cannot put a GPS coord on a butterfly yet. So here the typical observation model is the capture-recapture model. In this case, your observation model is probably that of GPS locations, maybe with some location error, which might be habitat specific because it's easier. GPS is better in open area than in a thick forest, for example. But conceptually, these are just variations of the theme, so you can think that, we don't yet have like general purpose software where you can just let's plug in this process model and this observation model. But maybe in the future we will have such flexible packages. Hopefully, maybe one of you will develop them for us. Okay, this is another way to draw the Bayesian state space models. We have the movement model, we have the observation model. Together they imply the distribution of the data, and then we have the priors for those. Let me now draw this same diagram for a concrete example, in which case we call it the graphical representation of this Bayesian model, which is called the directed acyclic graph, DAG. And this is really central for doing hidden Markov models or Bayesian state space models. I think you should always draw this DAG for your model. It helps you to understand kind of the links between the components of the model, but this will also be very useful when if you, for example, need to define MCMC schemes yourself, like for the parameter estimation, because this helps to understand like the links between the parameters. and the dependencies. So I think this is now pretty standard notation that by the circles you denote the parameters and hidden states to be estimated. So that in this case, this is just a correlated random walk model. We have step lengths, we have turning angles, they have parameters, like let's say we have 2 parameters for the model for step lengths, 1 parameter for the model for turning angles. So they are denoted by circles because, you know, these are parameters, scalars, these are like 2 numbers that we want to estimate. But the step lengths, they are also scalars, so it's like 1 number per step, but it's actually a long vector, all the step lengths that the animal took in the course of this study. And the same for these turning angles, it's like a list of all the turning angles. Now, if you know, let's assume that you know the initial location, that you know all these step lengths and the turning angles that were realized in the course of the study, then you actually know all the true locations. Okay, so in some sense these true locations, it kind of just repeats the information of the step lengths and turning angles. It's the same information, right? If you know these 2, you can figure out what are the true locations. If you know what are the true locations, you can figure out what are the turning angles and step lengths. That's why we have a dashed link here. It's a deterministic link. There is no uncertainty associated to that. Okay? So this part on the left-hand side, that's the process model. This is something that we can, for example, simulate even if we don't have any data. Let's assume that we have some data. So now the data is here in a box. Data in this case are the observed locations. I denote them by Y. So a square that denotes fixed quantities, I mean things that we don't estimate, for example data or some other fixed quantities. Let's assume that we can't observe directly the true locations. This is, for example, GPS data, and we want to account for observation error, location error in the GPS. So in that case, the data that you observe, like the location, let's say at time t, I mean the observed location at time t would be like the real location at time t plus then some observation error at time t. Okay? So in this circle we have the observation error. This is again a vector or list of all observation errors, I mean for all locations. So you see that the data depends in a deterministic way on the true locations and the observation errors. If you know these 2, you can simply sum them up like that, and then you get the data. Okay, that's why we have dashed arrows again. And then we assume that there is some model for the observation error. There is, in this case, I put there 1 parameter for that model. So to make this a bit more concrete, let's put here specific distributions that you might assume. For example, these step lengths you might assume that they have a Weibull distribution with these 2 parameters A and B. Turning angles might have this von Mises distribution. I'm now fixing here this 1 parameter to 0 because I assume that it's symmetric around 0. Okay, you could of course release that assumption, but I'm now making that assumption. That's why I have only 1 parameter. And then I assume here that the observation errors, they are normally distributed around the present location. Actually, this is a bivariate normal distribution. So D in this case is the variance parameter. This bold I just means a 2 by 2 identity matrix. Any questions about this?
What is the connection between true location Z and the data? Why did you put the dash in?
A dashed arrow here.
Yeah.
That's because the data that you observe is like the true location plus this observation error, the GPS error. Okay, and this is a deterministic equation. If you know these two, you know this one. Or more generally, if you know any two out of these three quantities, then you know the third one. So this is deterministic. Okay, that's why these two links arrows are dashed. It means that it's a deterministic link. So it's a different thing, let's say, from this link. If I know A and B, exactly, I know these two parameters. I don't know all the step lengths. They are still random variables. There is a stochastic link. Okay? But this link there is deterministic.
GPS allow you that there is a result around the true location.
Yeah.
So it's not if you know you cannot know the precise location. You know the
Yeah, that's an important point. I mean, here we assume that this is like conditional on knowing those errors. If you would exactly know the specific errors for each case, then this is deterministic. But there is a stochastic link here. So this D, you can think that that's like the, you know, I'm assuming that the GPS errors, they are like Gaussian distributed with some variance. Okay? What you are saying that even if I know that variance, like what's the typical size of GPS error, you don't know what are the realized errors, right? That's why we have a stochastic link here, okay? But if you would know these realized errors, then the data is a deterministic function of these two. So this is just a way to clarify the dependencies between the parameters. And some of the links will be deterministic, some stochastic, and it's important to understand which are which. But I mean, when you look at this graph, you shouldn't yet think what you can actually see in the data, what you can estimate, what you can't estimate. This is just like a logical graph of how the parameters depend from each other. And for example, the fact that this is a deterministic link is simply explained by this fact here, that this is just a deterministic equation. Okay, in reality you don't know these and you don't know these.
It's acyclic because you're not filling back the parameter.
Yeah, that's an important point. That in this graph you have these kind of places where you start. I mean, there is no arrow pointing to these parameters. Okay, and to all such parameters where there is no arrow pointing to them, you have to define a prior for them. Okay. And then there is no loop. It's acyclic. You don't go back there. Okay, and all state space models you can visualize in this kind of a way. Okay, let's then go through some basic concepts that are central to Bayesian inference. So we have parameters, data, prior, likelihood of data, and posterior. How many of you know earlier, I mean from your earlier studies, what these actually mean, or are familiar with these? I see a lot of hands like this. Okay, so parameters are the things that we want to estimate, okay, that we don't know about, which we want to estimate. And usually you denote them by theta. So you just collect all the unknowns of the model into this parameter vector theta. So in our model we had these four parameters, A, B, these are the parameters of the Weibull distribution, turning angle distribution parameter, and this is the observation model parameter. But additionally I put there Z and Z, where in this case the vector of all the true locations. Okay, so this is like the hidden truth. This is also something that we don't know. So in this case we put it to the parameters. It's actually something that we will estimate. So in the end we will have an estimate of the true location for every single step.
So why don't you put epsilon there as well?
Yeah, that's a good point. I could put there epsilon. I mean, we have this deterministic link. And so the idea is that if you know, I mean, why you know, that's your data. Okay? If you know Z, then you also know epsilon. Okay? Or vice versa, if you know epsilon, you know z. So you can choose which one of these you plug as a parameter, but you don't want to put both of them because they are just equivalent. Yeah, redundant. So I just chose to put z there as my parameter, and which one you put there, I mean, doesn't matter, but it might matter in the sense that the way you do the estimation might be more convenient with some choice. So this is clear. Y is the data, so the observed locations in this case. Then we have this prior. So prior is something that we set to the parameters. So it's for all of these outer parameters here, we just make up a prior in some way. I mean, I will talk more about that, like how you make up the prior. But like in this case, for these true locations, which is part of my parameter vector, you don't make up the prior because the prior for that is given through these links here. Okay. So what I denote by P, that's the probability density. So this is something that Luca was talking about quite a bit. So again, here you need to understand what's the link between a probability distribution and the probability density. Okay, let me try to clarify that once more. So let's say that we have a random variable x. This might be, let's say, normally distributed with some mean and some variance. So this you read like x is distributed normally with those parameters. Okay, so this is a probability distribution. For example, you can sample from it. But then it has a probability density. I mean, all probability distributions have a density. So in this case, the density of at the given value of x would be e⁻ x minus mu squared divided by 2 sigma divided by square root of 2 pi sigma. So this is the density of this distribution. All right. And the property of the density is such that if I integrate it over all values of x, then I'll get 1. So all probability densities, they integrate to 1.
So what's the difference between the two? What is the difference between the two?
These two. It's just the, let's say, notation. So, I mean, they represent the same thing. If you have a random variable which has this density, then it's distributed normally like this. If you have a random variable which is distributed normally with these parameters, then it follows this density. So they are equivalent. But it's kind of important to use the right term. You don't say that you have a x is distributed like this. I mean, that's a wrong way to say it. If we look at this here as a function of x, we see that what's below doesn't depend on x at all. So we can say that this is proportional. This means proportional to e⁻ x minus mu squared divided by 2 sigma. And this is something that we need to do often when we do some derivations. We look like which part of the probability density or some expression depends on the variable that we are interested at that time, and then we drop everything else out. Now this thing here integrates to 1. This doesn't anymore integrate to 1 because I left the normalizing constant out. Okay. Okay. Then we have the likelihood of data. So this you can read like this is the probability of observing the data given the values of the parameters. So if the parameter values were would have some specific values, theta. What would be the probability of observing exactly the data that you observed? This is what this likelihood function is telling about. What we actually want to get is something called the posterior distribution. Okay? Posterior distribution of the parameters. What I denote here is, just to use the right terminology, not the distribution itself, but the density of that distribution. Okay? So you can read this like, what's the probability of a certain parameter combination theta given the data that you saw. Okay? I mean, this might be probability density in case of continuous parameters, but I'll just use the word probability in a bit sloppy way. I will illustrate this in the context of a concrete example, but if you have any questions at this stage, you should ask. Okay, so this is the density of the posterior distribution. It is like, what is the probability that this parameter vector has some certain specific value theta conditional on the data that you observed. So you can, I mean, this is your estimate of the parameter. This is what comes out from that MCMC algorithm that you were running yesterday.
Why do you define the likelihood of data according to the observed location and the location?
Why do I define the likelihood of data in terms of the observed locations, not the true locations?
Because to calculate the likelihood of data, you need to also consider the distribution of the function connected to the true location and the observed location.
Yeah, that will become hopefully more clear later when I show how this decomposes to different components. But the fact is that what we observed is y, not z. So this is something that we can write down, as I will show. What is the likelihood of observing exactly this data y if we know the model parameters?
So the trial is a distribution and the likelihood and the posterior are probabilities? So they are both?
No, they are all distributions, and for all of them you can write down a probability density. Because as I said, for every probability distribution there is a corresponding probability density. Okay, they are just two ways to describe a distribution. You had a question as well?
First likelihood is not probability. It's like,
well,
and I think that you should mention that the posterior, that it can be probability density or probability, it depends if you normalize it or not, but it combines the likelihood and the prior.
Mm-hmm. Yes, I mean these can be probabilities or probability densities to start with, depending if you work with a discrete variable or continuous variable. Okay, so for a discrete variable,
the likelihood is not sample one. Probability. It's proportional to a probability, but not sample one. But I think it should be mentioned that the posterior is actually based on the likelihood and on the prior.
Yes, that's on the next slide, I think. I will mention that in the next slide. But I mean, this, just to come back to the likelihood, in some cases it can be a probability. Okay, like if you work with discrete variables, then it's the probability of observing exactly this data. And there are ways to, in some sense it sums to 1, but we can come back to that later. So, as I said, this is something that we want to have. This is like the posterior distribution of the parameter or the density of that distribution, conditional on the data. This is the so-called Bayes theorem or Bayes rule, but it's nothing else than a basic formula for conditional probabilities. It's saying that this density is proportional to the likelihood of the data times the prior. Okay? And so it's easy to derive where it comes from. So I guess many of you are familiar with this idea that the probability of, like the joint probability of, let's say, two variables x and y is the same as the probability of the variable x times the probability of the variable y given x. Okay? This is basically like the definition of conditional probability. Almost. I see that. You would like a more exact definition, but no. Okay, so what we have here is the joint probability of theta and y, which is the same as the probability of y times this probability here, this conditional probability. So this first equality comes simply from the definition of the conditional probability. And then I just split this in another way. I write that this is the probability of theta times the probability of y given theta. Okay. And what we are interested here is on the probability of theta. Okay, so we are interested about this thing as a function of theta, not as a function of y. So that's why we can drop this lower part here, because it doesn't depend on theta. That's why we have this proportionality sign. Okay, so what we would like to do is to sample the parameter vector theta from a distribution which has a density which is proportional to this expression here. And these two components you can write down in many models. So you can explicitly write down what is the likelihood of observing the data y given the parameter vector theta, as I will show soon in an example. And then you assume some prior, you can write down again explicitly as a mathematical expression what is the probability of a given parameter vector theta. So in a sense everything is kind of clear. After you have defined your model, you can write down what's the posterior density. But there is a technical problem that it's very difficult to sample from this distribution in practice, because like this can be a complicated expression. It's not like some standard probability distribution anymore. So it's difficult to work with that. One part of the problem is that there is no equality here. We don't know the normalizing constant. But this is the density of the distribution from which we want to sample. Okay? And now we just need a method how to sample from that. And in some special cases, this expression that you get will be very simple and you can sample directly. But in most cases that we work with in practice, we need to rely on some MCMC methods. Markov chain Monte Carlo methods that I will talk about in more detail. But I mean, not to avoid the impression that Bayesian methods are all about these complex MCMC schemes. To avoid that impression, I'll just show you some special case where you don't need MCMC at all. You can just do things directly.
What is the acronym MCMC?
Monte Carlo Markov chain. That comes up when I describe those methods. So this is an example of a simple model for which the posterior can be sampled directly in an easy way. So let's assume that you have binomial data, so that you have n trials, and then you observe y successes, like you flip a coin n times and you observe y times the outcome that you want to get. So you have a binomial model with the parameter theta. And let's assume that this theta is now the parameter that you want to estimate. So So in this case, you can, you can write down the DAC if you like. You have here these parameters. You have a prior for, no, that's not right. You have a prior for this theta, which I define as a beta distribution, just for the sake that it's mathematically convenient. Okay? So we assume, before we see the outcome of this exercise, we assume that this theta is beta distributed with some parameters. Okay? And just to illustrate how the prior might look like, the typical prior is that I say that, these two parameters I don't estimate, I just make them up because this is the prior. Let's say that I say that A is 1 and B is 1. Okay? In that case, the beta distribution is flat. This is how it looks like. It's the red line. That's the beta distribution, which is defined in the interval between 0 and 1. So it's appropriate for probabilities. And it's just a flat line. This is like a uniform prior. It means that I don't basically assume anything. I assume that all values are equally likely. But I can express that as a beta distribution, beta 1, 1. Okay? Now, if you make these assumptions that theta is beta distributed with some parameters, that's your prior, and then your likelihood follows this binomial distribution. If you just write down this expression, write down all those densities, density of the binomial, density of the beta, and you work out how this looks like. If you like, it's a simple exercise. I'm certain you can do it yourself. You will observe that what comes out also has the form of the beta distribution. Okay? So in that case, the posterior will also be beta distributed with these parameters, a plus y, b plus n minus y. So you can think that this is just some kind of a mathematical miracle that in this specific case this just happens, that it comes out as a beta distribution. Okay, that's why beta is called the conjugate prior for binomial, because if you start from that prior, also the posterior will have the same form. Okay. So what I did here was to generate some data. I assume that I do 100 trials. And then this probability of success is 0.3. So I'm saying that y, the data, is a random draw from a binomial distribution with these parameters n and 0.3. In this case, it gave me 27 successes and 73 failures. Typically you should get 30 successes, but there's randomness because it's a random process. And then I just write down the expression for the beta distribution. So now y is 27, n minus y is 73. And then I have here 1 plus, and this is 1 plus because that was the prior. And then I plot what is the probability density of the posterior distribution. That's the blue line. Okay? You see that it's kind of concentrated close to 0.3, which is the true value. And then the width shows the amount of uncertainty. The peak is not exactly at 0.3 because in this case 0.27 is what looked like the most likely value. But the width 0.3 nicely falls within the core of this distribution. So this now illustrates the concepts of the prior and the posterior. Prior is what we assumed about the parameter value before we saw this data. In this case, we didn't basically assume anything. And the posterior is what we think the parameter value might be, what's the distribution of the parameter value after we have seen the data.
Can we just say a little bit about the beta distribution?
It's just a probability distribution which depends on two parameters, which has its support between 0 and 1. So if you randomize values from that, you will always get something between 0 and 1. And that's why it's kind of a handy distribution if you want something that produces probabilities. But if you type beta distribution, you will find a Wikipedia page which shows how it looks like and for what is it useful for. But we are not using beta distribution in any of the examples here. This was just an illustration that sometimes you can figure out analytically what is the posterior distribution. Okay, but then these Monte Carlo Markov chain MCMC methods, they are often needed for more complex models as this one. Because if for this model, let's say we would do the same exercise, we would write down what is p theta given y. I mean, we can do it. It gives us, we can write down analytically what these are, even for that complex model. But it will be some long expression. If you stare at that for a while and then you become frustrated, it doesn't look, like normal or anything like that. It's just some expression, and then you don't know how to work with that. And that's why you need these MCMC methods. And the basic idea in all of these methods is to construct a Markov chain. I mean, that's the Markov chain part of the name. How many of you know what is a Markov chain? Ran, I hope you know. Yeah. So a Markov chain is a stochastic process where you, let's say in this case, you start from some value of the parameter vector. You have a stochastic link that if you know the current value of the parameter vector, you can randomize the next value of the parameter vector. Okay, and once you know that value, you can again randomize the next value of the parameter vector. So Markov chain doesn't have memory. It means that it's enough to know the current state to randomize the next value. So here we do the Markov chain. I mean, like if you write down a random walk model for the animal's location, that's often a Markov chain for the location of the animal. But actually here we are doing a Markov chain for this parameter vector. Often in some of the methods, as I will show this, the entire parameter vector is actually doing a random walk. And the key idea is that it's possible to construct such a Markov chain that the stationary distribution of that Markov chain is exactly the posterior distribution that you are seeking for. So a little bit more sloppy way to say that is that the Markov chain converges to the posterior distribution. Okay? So in an informal way, what is the stationary distribution? It means that you run the Markov chain for a long time. Okay? It converges to something. Like, let's say that we have only one parameter theta, so that I can illustrate it. You start somewhere. This is like your iteration round 1. I start from here. In iteration round 2, it maybe jumps somewhere. Then iteration round 3, it again jumps somewhere. Often it's doing some kind of a random walk. And then you continue. And maybe it looks like this. So it doesn't converge to a single value. It doesn't kind of stop. But it converges to a stationary distribution, meaning that at long times, if you drop what happened initially, the statistical properties don't change anymore. Okay? That's the stationary distribution. And as said, it's possible to construct the Markov chain in such a way that this stationary distribution is exactly the same as the posterior distribution that you are trying to sample.
So there is always a hidden assumption that there is no memory in the system when you do this.
In which system?
In the original system, because you assume it's a Markov chain one memory.
No, I mean your movement model, for example, can very well have memory. Okay, the model can be anything. What we are doing here is nothing that relates to the model itself. This is just a technical tool how we sample this posterior distribution. Okay, And you know, people have just figured out that it's possible to construct these Markov processes, Markov chains in such a way that it gives the right answer. I will give examples of how that's done in practice. But this Markov chain here has nothing to do with the original model. I mean, except that these transition probabilities, you derive them from the model. But like one of these parameters could very well be like the amount of memory. Okay, and what we did in the exercises was to actually use an R package, which kind of does everything for you. You don't need to know how do you sample the posterior. You just run it with this MCMC package. But it's and it's fine to do it. Of course, I mean, you don't need to turn into some statistician or computer scientist to mathematician to use these methods. But I think it's important that you understand the basics, like what's inside that black box, and that's what I'm trying to illustrate now. And what's useful to do is to decompose that posterior likelihood into different bits, and usually that's nice to do using this DAG as a kind of a machinery or advice how to do it. So just to recall, in this case, the parameter vector theta contains these 4 real parameters A, B, C, D that we are interested about, but also all of these hidden true locations. And we have these 2 components that we need: the prior, the probability of theta by itself, and then the likelihood of the data. Okay? If we first look at the prior, just the probability of theta, we see that I have here in this outermost node 2 parameters, A and B. Okay? This means that I might define a kind of a joint prior for them. Sorry, let's start from the simplest. Here we have just one value, C. Okay? It's not linked in any way to A and B. Okay, so this actually means that I decided to define a prior to C independently of the other values. That's why here in the expression for the prior, we have the probability of C as one component in this product. Okay? And in the same way, we have the probability of D. Because this is like the joint probability of the full vector A, B, C, D, Z. But as we assume that like C and D are independent, we can write that part of the joint probability just as a product between C and D. Okay? But we might want to define some joint prior for A and B. That's why I wrote here P, A, and B. I mean, there is no reason for doing that in practice, at least I guess in this case, but just to illustrate, your prior for, let's say, C could look like this. This would be the density for the probability. Density for the distribution. But then you might want to define a joint prior for A and B. Let's say that you define a bivariate normal distribution, but you want to include some correlation, so that these would be like the quantiles of that distribution. I mean, there is no reason doing it here, but sometimes you might want to do it. So in this case, this would be a joint prior, which means that you cannot write it like PA times PB.
But they are not independent.
They are not independent, yeah. So basically, when I'm decomposing the probabilities, I'm looking at what is independent and what is not. Okay? So now I have dealt with all of the parameters, A, B, C, and D. What remains are the true locations. So I can write here the probability of the true locations conditional on all the parameters. And So this is the probability. I mean, originally I write there probability of Z conditional on all the parameters A, B, C, and D. That I can do just, you know, by the definition of the conditional probability. But then I look at this graph. I look what Z is really depending on. Okay? So I follow these arrows backwards from Z. I get to A, B, and C. I don't get to D. So conditional on values of A, B, and C, Z doesn't depend on D at all. Okay? That's why D doesn't appear here. Then we write down the likelihood of the data. So this is the probability of observing Y given theta, where theta now again has all these A, B, C, D and the true locations. This we can also simplify. Because if we know theta, so we know A, B, C, D and Z, what does the data depend on? So you see where the data is coming from. The data depends on Z and this observation error epsilon, which in turn depends on D. So you see that the data depends only on Z and D. It doesn't anymore depend on A, B, C. Because if you know Z, in that case you don't need to know those values to figure out what's the likelihood of the data. Of course, if you wouldn't know the true locations, then the likelihood of data would depend on those parameters. But conditional on the whole vector, you can drop out A, B, and C. So this is a reason why I think this DAG is really useful, because when you draw it correctly, you can kind of follow simple rules to see how these expressions simplify, what you can drop out and what not. And next, you simply write down the posterior density of the parameter theta given data Y, which is a product of these two. So here I have done nothing else than just multiplying this expression by that expression.
Because the Z equals Y, okay, you have no observation. How would these equations look like? Because here you sort of consider Z as one of the parameters, right?
Exactly, yeah. That's one of the parameters that I'm estimating.
I mean, how would it look like if Z equals Y?
Okay.
No observation.
Let's consider that case. Soon. I mean, it comes here later that we actually do that case in practice. This is how it looks like. Okay? So in that case, you simply don't have this observation part of the model. Your data are the observed true locations Z. So it simplifies, but you can still draw it in the same way. Just the right-hand side drops off.
Okay. The equation, how the prior is defined, then will not be within this prior anymore.
Sorry?
The prior, the probability of Z is actually the probability of Y.
Yeah.
I need Z from the prior.
Yeah, then this part actually comes, this part here, which is now part of the prior or and the process model, comes here as the likelihood function. Okay, one more concept that's kind of central here is that of the full conditional distribution. So the full conditional distribution is defined, for example, in this way. This is the full conditional distribution of the parameter B, one of the parameters of the model. So this is asking that what's the distribution probability. Let's speak a bit loosely. What's the probability of a given value B given the data and given the values of all the other parameters. That's called the full conditional distribution. So if you would know not only the data, but if you would know, let's say, the true values of all the other parameters or some values of all the other parameters, in that case, what would be the probability distribution for B? This is the full conditional distribution of the parameter B, given the data and all the other parameters. Okay? This is just the definition. Later you will see why this is useful, but this is just the definition. And in this case, we can write down that this full conditional is proportional to the probability of this prior AB times the probability of Z given ABC. To get this expression, you just look at the full posterior distribution or the density of that, which I wrote down in the previous slide. So this is the expression that we had already. Now we are interested in the parameter B in this case. So you just check that expression, see where the parameter B appears. Which part of that expression depends on the parameter B. So you pick that part up, and that's what gives you the density, full conditional distribution of parameter B.
Can you repeat this step? You selectively chose the places where B was mentioned in the previous paragraph, the previous formula?
Yeah, so I go through this, I see that, okay, B appears here, I have to take this into account. B doesn't appear here, so this is kind of part of the normalizing constant, I can drop that out. Doesn't appear here, but it appears here, so I have to lift this in. And again, it doesn't appear here in the likelihood expression at all, so I can drop that part out. That's again like, if you think of B, then this is part of the normalizing constant. If you think of some other parameter, this might be more relevant.
If it was, for instance, a C here, so you wouldn't take the AB, you would take the C. That's the only replacement you would have done.
Exactly, yes. So you can define these kind of full conditionals for any of the parameters of your model, or then you can define the full conditional also for parameter combinations. For example, you can ask that what's the full conditional distribution for parameters A and C, or whatever parameters, like a joint distribution of these, given all the rest, like Y, B, D, Z. Using the same logic, you can write down an expression for that. What time is it? Should we have a break?
It's 11:45. 11:45.
So you want to have a break now, or just continue in one go? Break. Okay, let's have a 10-15 minute break.